What is up, my people? Welcome back to another video lesson. I am Mr. Kozad. I'm so happy that you're here. Before we get any farther, I gotta tell you, today is a great day to be alive. I'm thrilled that you found this video, whether you're watching it because you want to or you have to. Welcome. You are welcome here. I hope that you find it helpful. Our topic for today is a fun one, a really fun one. It's exponential and logarithmic word problems. Some of the things we're going to specifically look at is we're going to look at a new equation for my students, PERT, and we're going to talk about half-life questions. So if those things are interesting to you, let's jump right in. So here we go. First disclaimer that I have to give you is that it is impossible to show you every type of problem that you're going to see. I can't do it. It would take all the hours and all of the YouTube bandwidth to be able to go through that, and we can't do it. It's impossible. So here's just a sample of what you can see, and man, I hope that you enjoy it. Okay, it's going to be fun. So here we go. Get a paper and pencil, and let's talk about this new form of an equation that we're going to use for continuous, keyword continuous, growth or decay. So yes, this is a new equation, but a lot of the variables are going to be the same as discrete growth or decay, which we talked about when we did like those problems with like compounding interest over different intervals of times, different compounding periods. Okay, so what we're going to talk about with A is going to be the future value, the value of something in the future, not today, but at some point in the future. P is going to be the present value or the current value or today's value. Okay, so A is the future value, what you have after a certain amount of time. P is the present value, what you currently have or what you're starting with. Okay, R is the growth or decay rate. Depends on what the problem is, and it'll tell you in the problem. You'll see that in just a minute. One note that I'm going to kind of add here is if it's growth, the rate will be positive, and if the problem is decay, the rate will be negative. Again, you'll see that as we start to work through some problems here in just a minute. And T, you probably would have guessed that. That's just going to be our units of time. Okay, so these are the variables we're going to use. And just if you don't really remember what I was talking about with discrete growth or decay, that's where we talked about the present value times 1 plus or minus the rate to the t power, or with the financial applications that we did 1 plus r over n to the n times t power. Those are the other equations that we talked about, but PERT is the one we're going to talk about today. Yeah, it's called PERT because if you look, it spells PERT. Okay, I don't know. That's how I learned it. I don't know if teachers still teach it like that anymore, but I do. So it's cool to call it PERT. So I'll probably say that a lot on accident. You can just know that's what I mean by that. Okay, so here we go. Let's jump right into some problems together. So example 1, the amount of pollen is increasing continuously. Underline that word continuously. That's important to know. Let me get the pen. Continuously. Okay, that tells us that we can use PERT at a rate of 2.5% per day. If there are currently 250,000 units of pollen in the air, how long will it take for there to be 700,000 units? Okay, so we're going to write our equation. Okay, I'm going to write it a few times until we remember it. A equals PERT. A is the future value. Now, in this scenario, our future value is 700,000 units of pollen. Our present value, today's value, is 250,000. So that's going to be E to the R is the rate. So again, it's growth, so it's going to be positive. We're going to write that as a decimal, 0.25, and T is what we're trying to find. We're trying to figure out how long it's going to take for those 250,000 units of pollen to turn into 700,000 units. Okay, so our first objective here well, we already did our first objective. That's to write the equation. But the next thing we want to do is we want to isolate this exponential term. So divide both sides by 250,000. So when you do that, when you divide both sides by 250,000, 700,000 divided by 250,000, I'll let you type that in a calculator if you want. But it gets us 2.8. Okay, it gets us 2.8. So we have 2.8 equals E to the 0.025 times t power. Now, to solve for t, we're going to have to write a log equation, okay? And because we have base e here, we're going to write a natural log. If you'd like to know more about natural logs, there's a lesson, the previous lesson walks you through what is a natural log, what is base e, and how to deal with those. So we're going to take the natural log of both sides. So that's going to be ln of 2.8 equals 0.025 t. Okay, so this now very quickly turns into a graphing calculator problem. If you have a graphing calculator, get it. If not, you can go to actually desmos.com and type in a lot of these calculations and it'll do that for you. Or there's several other things that you can find online that'll help you evaluate these. But what I'm going to type in my calculator is I'm going to type in ln of 2.8 and make sure you close that parenthesis. And then we're going to divide both sides by 0.025. So it'll be ln 2.8 divided by 0.025. And for me in my class, we like to round to 3 decimal places. So when we do that, we get 41.185 days. It's always important in word problems to have a unit attached to your answer. So it's going to take about 41.185 days for this event to occur. Okay, so that one's pretty easy. Let's try another one. Okay, here's number 2. The population of lions is increasing at a rate of 0.8% per year, and a population of antelopes is decreasing at 3.1% per year. I'll let you connect the dots and try to figure out what's happening here. It's not pretty, but it is all part of the great circle of life. You see, Simba. I won't do my Mufasa impression. This is weird, especially when I'm in a room all by myself. So thanks for not turning off the video if you haven't already. So here we go. Let's write some equations here. So we have 2 events that are happening, 2 populations that are changing. Okay, so let's start by writing an equation for the lions. Okay, so the lions, we need to know... we don't know what the future value is going to be, but we know that our starting value, we're starting with 25 lions. So 25e to the rate. Now be careful on this rate because you need to write it as a decimal, but it's a 0.8%, not 8%, so you need actually 2 zeros there. And again, we don't know the amount of time that we're looking at. Okay, so then let's write another equation for the antelopes. So we have A, the future value. We don't know what the future value is because we don't know the time. But we know we're starting with 300. E to the decreasing. So remember when we talked about this, the rate should be negative. So negative 0.031 times t. Now, the question's asking you at what point in the future, so we're looking for a time, will the populations be the same? So what that's asking you is say, sometime in the future, these values, the future values, will be the same. So if this A is the same as this A, what can we do? You're right, you can set them equal to each other. Okay, so if we set these equal to each other, we get 25 e to the 0.008 times t equals 300 e to the negative 0.031 t. Okay? Now, this algebra gets a little spicy here, so I'll try to go as slowly as I can, but you might need to rewatch some of this another time. If you're on your phone, you can just double-click to the left, and it'll go back 15 seconds. Rewatch this as many times as you need. I'm going to go kind of quickly through this algebra. But basically, I want to get the constants on one side and the e's on one side as well. So the first thing I'm going to do is I'm going to move this 300 to the other side by dividing. And then I'm going to take this e term on the left, I'm going to move it over to the other side by dividing as well. So when I do both of those things, here's what we end up getting. We get 25 over 300 equals e to the negative 0.031 t all over e to the 0.008 t. Okay? I'm running out of room. I'm going to have to be creative here. Okay, so then we can do a little bit of work here. We can actually do some division. So let's divide 25 by 300. When I divide 25 by 300, I actually get 1 over 12. And remember your properties of exponents here, okay? Properties of exponents say if the base is the same, base e on the top and base e on the bottom, we can actually subtract the exponents. So I can combine that into one term as e to the negative 0.039 times t. Again, we're just subtracting the exponents because that's what you do when you have the same base in the numerator and denominator of a fraction. Okay? All right, so then the next thing we're going to do is we are going to write this as a log equation. So we're going to do ln of 1/12. Oh no, I'm very running out of room. Let's see, so sorry about that. I didn't plan this very well. Let me try and move this up here. And then, yeah, I should be able to squeeze it in. Okay, so let's write this out as the ln of 1/12 equals negative 0.039 times t. So again, this turns into a graphing calculator problem. You're going to take the natural log of 1 divided by 12, and then divide that number by negative 0.039. And when you do that, what you're going to get t is approximately 63.716 years. So it's going to take some time, but in 63 years, there will be exactly the same number of lions as there are antelopes. Okay? And then after that, unless something changes in the circle of life, the lions are going to keep growing, and the antelopes are going to keep dwindling. Okay, so 63 years is when the populations will be exactly the same. Okay, next question. Okay, example number 3, radioactive substance decaying. These are probably, decay of radioactive materials is probably one of the most common Algebra 2 application problems in this content. So if you're not one of my students, this is probably a question that you've seen in your class or on your homework. So pay attention. So decays continuously, those are both important words. Okay, decays continuously, both important, at a rate of 3.4% per day. Okay, how long will it take for only 25% of the substance to be remaining? Okay, this is a little weird. Okay, so what we need to do here is we need to figure out what this is talking about with 25% of the substance remaining. Well, what that means is that A, the future value, is going to be 0.25 of today's value, the present value. In other words, we could write that as A is going to be 0.25 times P. Okay, so if we build our equation, we know that we can replace A with 25% of what we start with, and that equals what we start with times E to the 0.034, and we are solving for the time. Okay, now you might be asking yourself, well, Mr. Cosette, don't we need to know how much of the substance we're starting with? And actually, no, you don't, because you know that what's happening here is you're going to have 25% of whatever you start with left over. So algebraically, whatever that amount is would actually cancel out on both sides. It doesn't matter. So what we can do here is we can cancel out that variable. So we just have 0.25 equals e to the 0.034 times t. So now we're going to write this as a natural log. We'll do natural log of 0.25. That equals 0.034 times t. And then this turns into a graphing calculator problem. We're going to take the natural log of 0.25, and then we're going to divide that by 0.034. And as you do that, you should, oh man, I made a huge mistake and somebody probably caught it. I'm glad I caught it now and didn't have to wait for you to kill me in the comments. Man, I know somebody got it. I even underlined it, the word decay. The word decay means that rate needs to be negative. How embarrassing is that? Oh, Cosette. I make one mistake every 10 years. Okay, and there it is right there. So that rate needs to be negative. Shoot the boot, my people. I'm so sorry. Okay, so let's make that rate negative, which means I need to sneak a little negative sign in here. Okay, I'm so sorry about that. How embarrassing. So now we take natural log. That's okay. Even the great ones make mistakes. So we take the natural log of 0.25 and divide it by negative 0.034. And we get our time to be 40.773. And what was our days? What was our time unit there? Days. 40.773 days. Okay, pretty easy. Next question. We just have two more, by the way. Two more questions. You're almost there. Example 4, the half-life, underline that, we'll talk about that here in a minute. The half-life of a radioactive substance is the time it takes for half of the atoms to disintegrate. The half-life of carbon-14, very common carbon molecule, is 5,730 years. It says determine the value K of, and the equation of decay for carbon-14. Okay, so a couple things here. Half-life, very common application question. If you're a chemistry student, you probably actually have already learned this before. Maybe used a different equation than we did. Okay, sometimes I purposefully did this, the value of K. There are a lot of applications that instead of using the variable R for PERT, they use K, and they call it like the growth or decay factor, the factor of growth or the factor of decay. So the first thing that we have to do is take this information they give us about the half-life and work backwards to find the value of K. All right, so for half-life, you know that the future value is going to be 1/2 of whatever you start with, okay? So when you build your equation, you know that your future value is 1/2 of what you start with, and that equals what you start with times E. In this case, we're going to use K because that's what the problem asks us to do, times the time. Now, the time is actually given to us. It tells us the half-life is 5,730 years. So that's what we're going to use for our time. Now, if you paid attention on the last problem, you know that the starting amount actually doesn't even matter because it's going to cancel, because no matter what you start with here, you're going to have half of it left over. Okay, so it really doesn't matter. So then we've got, we can take the natural log of both sides. So we take the natural log of 1/2, and that equals 5,730 times K. So again, now this turns into a calculator problem. We're going to take the natural log of 0.5 and divide it by 5,730, and we get K to be negative 0.123012. There is the first part of the problem. We determine the value of K. And then the last thing that it asks us to do, and the equation of decay for carbon-14. So the equation of decay is just going to be a generic equation. So it's going to be the future value equals whatever the present value is times E to the negative 0.00012 times T. That is the equation that you're going to use. Again, I went fast through that. If you need to go back and listen to that explanation again, please do it. Feel free to send me a message or leave a comment if you'd like some more help on that. But it would help if you also go back and think about in example 3, this part here. This is the hardest part, is figuring out the relationship between the future value and the present value on examples 3 and 4. Okay, final problem that we'll do together is example 5. It says if a population of bacteria doubles every 8 days, how many units of bacteria would there be in 12 days if there are currently 120 units? What? I need to reread that. You probably need to reread it. A lot going on there. Okay, so this is actually a two-part question. Okay, this is a two-part question. So the first thing that you're going to need to find, if you read it again, there's nothing here that tells us what the rate is. So the first thing that we need to do is find the rate. Okay, find the rate. Okay, so let's write an equation with what they do give us. Okay, it says that the bacteria doubles every 8 days. It doubles every 8 days. Okay, so that means that our future value is going to be 2 times our present value if it doubles every 8 days. So if we build our equation, we know that our future value is 2 times the present value, and that equals the present value times e to the r. We don't know what the rate is yet, but we know that this doubling happens after 8 days, so our unit of time is 8. Okay, so again, if you've been paying attention, you know that the p's cancel. Okay, so then we take the natural log of 2 and set that equal to 8r. Then we divide, that turns into a calculator problem, so we get our rate. We take natural log of 2, and we divide that by 8, and we get 0.087 is our rate. Okay, now that we have the rate, we're ready to move on to part 2 of this problem. Okay, part 2 of the problem is to find how many units after 12 days. So let's build our equation using our rate. So we want to know what is the future value of these units of bacteria if today there's 120 units times E. There we go. We use that rate that we found in part 1. That's why part 1 was so important. And it says 12 days is our unit of time. Okay, so this is really easy. You don't even have to take the natural log of anything. You just plug and chug in your calculator. Plug this in, press enter, and see what you get. And you should end up getting 340.867 units of that bacteria after 12 days. Again, disclaimer at the very beginning was it's impossible for me to show you every single question. If you have a specific question about a specific problem that your teacher asked you to do or that you see in a homework or a worksheet or something, please reach out to me. Send me a note, send me an email, leave a comment on this video, and I'd be happy to help you out. I hope that you enjoyed this. I hope you found it beneficial for you, and we will see you next time. See y'all.